With the introduction of decision tree models, now we can introduce another important machine learning models, which is known as random forest. So random forest actually, before deep neural network models, random forest actually can achieve very good prediction performances among many existing machine learning models. You can consider the random forest as the combination of multiple decision trees to make predictions. So because that combination idea of combining multiple decision tree predictions to make the final prediction, random forest model is indeed one of the ensemble machine learning models. So you are trying to assembling multiple so-called weak learners to make strong predictions. Ensemble learning is another important research direction in machine learning. Random forest is one of the ensemble methods. And we will talk about something else when we move to the other sections. The idea of random forest is essentially we are trying to derive an ensemble of decision trees by this bagging procedure. The building blocks of random forests are indeed the decision trees. The algorithm of the decision tree models is essentially you are going to first trying to train multiple decision trees given a training data set. But this training procedure is doing a bagging sampling procedure, right? Instead of using the whole training data set, using all the number of predictors, variables, or features, you are going to sample them. You are going to bootstrapping, so basically you are going to sampling with replacement among the training data set to derive a new training data set. And then you are also doing, instead of using all the input features, you are going to sample a subset of features and only use this subset of features to derive the decision tree. Once you sampled the new training data set, once you decided the subset of predictors or features you are going to use to derive decision trees, you derive that decision tree and you repeat this procedure multiple times so that you can derive multiple decision trees. Once you determine the multiple decision trees, then you can make the final predictions based on either majority voting. So given a data point, you go to that corresponding decision tree, and if decision tree 1 make the prediction is a positive class, decision tree 2 also make the positive class, etc., etc., then you count how many decision trees are making the positive class prediction, how many decision trees are making negative prediction, and then you take the majority vote. So that's your classification prediction. And for the regression, again, you can do the average to get the final prediction. And as all the ensemble methods, this combination of the weak learners, so-called, has certain theoretical guarantee that this kind of majority voting or average of the weak learner predictions to combine them into the final prediction will give you better prediction performances. But if you want to kind of improve the prediction performances, then typically you want to optimize the bagging procedure by making sure that the correlation of different derived decision trees is going to be as small as possible. Otherwise, basically, those decision trees are making the same decisions. So it does not really help you. If the correlation is really, really high, then the final prediction may not benefit too much from deriving many decision trees. And then you also don't want the correspondingly derived decision trees to have really, really bad performances. And if the individual decision trees have really bad performances, then of course the final predictions will not do very well at the end. So at least in the boosting, bagging, and sampling machine learning models, for theoretical guarantee that the final prediction will be better, the individual weak learners or individual decision trees in random forest have to be performed better than random guesses for sure. This basically compares a random forest with decision trees. The commonality is that the random forest is composed of multiple decision trees. And decision trees, if you don't do appropriate regularization, they may suffer from overfitting. But random forest, because it is ensemble method, it is an ensemble machine learning method. Actually, you can kind of reduce the overfitting risk because you are actually doing the subsampling. You are subsampling the training data set with bootstrapping. You are subsampling the subsets of descriptors to derive the decision trees. And then you're also trying to borrow the strengths of multiple decision trees. So actually, that's why you can reduce the overfitting. And compared to actually decision trees, random forest is relatively more difficult to interpret because at different decision trees, the predictions are derived based on different subsets of features. So that's the reason why there is some level of difficulty to do the white box interpretation, but the researchers does derive the ways to rank the importance of the corresponding predictors in random forests and use them to derive the corresponding rules and the corresponding interpretability strategies to explain why this random forest is making the corresponding decisions. That's one of the important thing, and like what I said, random forest is an ensemble method, and actually there are different families of ensemble methods, and including bootstrapping, including boosting, including bagging. Random forest is a bagging ensemble method. So the bagging basically means that you sample both training samples and input features. And then boosting is essentially you are trying to derive weak learners using the whole training data set and then combine the derived weak learners in the boosting way. We will talk in more details for the boosting message when we go to the corresponding section later on. And the bootstrapping is essentially just handling the training data sets, trying to sample the corresponding training data points so that derives the corresponding models within the sampled data set, and then somehow you combine them. And the application here is essentially a plant example. So basically, you are trying to get the iris features as input predictors, and then you are trying to build up the random forest decision tree to classify the corresponding iris into different iris species. So those are the input features, right? They're basically the petal width, petal length, sepal length, sepal width, and then based on that, you're trying to tell which categories of iris plants they belong to. And basically, you can do both random forest or decision tree classifier, and you can compare the performances. So indeed, at least for this simple example, you can see that random forest can give a better performances than the decision tree. And you can do the same thing with the hard data, and you will see the same trend. The random forest give you better prediction accuracy than simply just derive a decision tree. Okay, you can do the quiz to evaluate whether you understand what's going on.